30 million years ago, the world's largest shark didn't just haunt the ocean, it ruled it. All that remains are teeth, scattered like secrets beneath the sea, some stretching over 7 inches long. Yet for such a titan, the trail is frail. The bones are missing, taxonomic debates rage, even its true name is unsettled. Scientists claim extinction, but gaps shadow every certainty. Why are our only witnesses silent fossils? And what vanished with them, besides fear? Here begins the investigation into the ocean's forgotten nightmare. Shark teeth are among the most durable objects produced by any animal. Each megalodon tooth is a relic of mineral and time, built from hard enamel and dentin that can survive millions of years underground. But the rest of the animal, the skeleton that once stretched over 60 feet, was made almost entirely of cartilage. Unlike bone, cartilage is soft, flexible, and rich in water. It decays rapidly after death, dissolving in mud or washing away with the tides. Even in the rare cases when cartilage escapes scavengers and bacteria, it leaves almost nothing behind for the fossil record. This imbalance shapes everything we know and everything we cannot know about Megalodon. Fossil beds across the world yield thousands of teeth, some as small as a fingernail, others as large as a human hand. But the jaws that held them, the vertebrae that powered the body, and the fins that cut through ancient seas, these are nearly always missing. Only a handful of vertebral centra, hardened by mineral deposits, have ever been recovered. Most are incomplete, eroded, or isolated from the rest of the skeleton. The chemistry of fossilization favors the teeth. Enamel resists acids and pressure, locking in shape and structure even as sediment buries it deeper. Cartilage, on the other hand, is almost pure collagen and water. It offers little for minerals to replace, and so it vanishes. This is why paleontologists find teeth in every ocean basin except Antarctica, but must reconstruct the rest of the animal from fragments and modern analogs. Every tooth carries information, a record of growth, feeding, and even water temperature locked in its isotopes. But teeth alone cannot reveal how the body was shaped, how the fins moved, or how the skeleton flexed in pursuit of prey. The overwhelming abundance of teeth creates an illusion of completeness. In reality, the evidence is lopsided, defined by what survives the long passage through earth and sea. This bias forces scientists to work backwards. They measure the width of a tooth root, compare it to living relatives, and build models of size and power from a single shard. The missing cartilage turns every reconstruction into an act of inference. What we know about Megalodon is filtered through the teeth, and what we do not know is lost with the vanished skeleton. The fossil record is not a window, but a keyhole. Teeth are our only reliable witnesses, enduring while the rest of the giant dissolves into the silence of deep time. Beneath the tidal flats of Chesapeake Bay, ancient bones bear silent scars. Whale vertebrae and rib fragments, unearthed from the Calvert Cliffs, display deep, serrated gouges, each trace a signature left by a giant predator. The spacing and depth of these wounds match the teeth that fill museum drawers, broad, triangular, and edged like saw blades. Forensic comparisons reveal a close fit. The arc of a megalodon tooth aligns with the grooves carved into Miocene whale fossils, the serrations leaving a ragged edge that no other shark could produce. These marks are not random. Some bite traces encircle the midsection of a whale, as if the attacker aimed to immobilize with a single, crushing bite. Others slice across flippers and tails, hinting at a strategy of disabling prey before feeding. In one case, a whale vertebra from the Chesapeake group preserves a gouge so wide and deep that only a tooth over 6 inches long could have made it. Tooth and bone together form a record of behavior. They show not just what Megalodon ate, but how it hunted. The evidence suggests a predator capable of targeting the largest animals in the sea, striking with force and precision. Yet even as bite marks offer a glimpse of life and death in ancient waters, the fossils themselves raise new questions. The teeth that leave these traces are easy to recognize, massive, robust, and often bearing fine serrations along the edge. But naming the animal that wielded them is not so simple. For decades, the giant shark was classified as Big Was Megalodon, grouped with the great white and its kin. Recent studies, however, challenge this lineage. Detailed analysis of dental morphology, root shape, crown thickness, and the pattern of serrations suggests closer ties to the extinct genus Otodus, a line of mackerel sharks that diverged from modern great whites millions of years ago. The debate is more than a matter of labels. If Megalodon belongs with Otodus, its evolutionary story shifts, and so do the assumptions about its behavior and biology. At Lee Creek Mine in North Carolina, a single tooth, wide at the base, sharply serrated, became a focal point for this controversy. Some researchers argue its features fit better with Otodus than with Carcharodontes, blurring the boundaries between families. The disagreement runs through scientific papers and museum collections, reflected in shifting catalog cards and revised display labels. Every fossil carries a name, but sometimes the name is provisional. The bite marks in Chesapeake bone and the teeth from Lee Creek are clues, not answers. They remind us that the story of Megalodon is still being written, shaped by every new discovery and every unresolved debate. On a laboratory table, a single tooth sits beside a digital caliper. Its root is as wide as a grown man's palm, its serrated edge still sharp enough to draw blood. From such fragments, researchers attempt to resurrect the full scale of the animal that carried it. The process begins with measurement, precise, methodical, and grounded in comparison. Each Megalodon tooth is cataloged by root width, crown height, and curvature, then plotted against the jaws of living relatives. The great white shark, Carcharodon provides the closest living analog, though the lineage is debated. Scientists use statistical regressions to translate tooth size into body length, drawing on hundreds of specimens from both extinct and modern sharks. These formulas are not guesswork, they are built on decades of data, refined with every new fossil and every scan of a modern jaw. Yet the numbers never settle into a single answer. The largest Megalodon teeth suggest a shark that reached up to 20 meters in length, about 65 feet from snout to tail. Most estimates cluster between 15 and 18 meters, but every calculation carries its own margin of error. The width of a tooth root can vary with age, sex, and even the position in the jaw. Some regression models use only the largest anterior teeth, others include side teeth or even partial fragments. Each choice changes the outcome, sometimes by several meters. Researchers publish their methods alongside error bands, acknowledging the uncertainty that shadows every estimate. Advances in imaging have pushed the boundaries further. In recent years, CT scans of rare fossilized vertebrae, discovered in places like Belgium and Japan, have allowed paleontologists to reconstruct segments of the spinal column in 3 dimensions. These vertebral analogs, when compared to the skeletons of modern sharks, help refine mass and length estimates. The results suggest a slightly more slender body than the classic museum models, with long pectoral fins and a broad, powerful tail. Computer modeling fills in the missing cartilage, extrapolating from the preserved centra to imagine the sweep of the backbone and the span of the fins. The largest reconstructed vertebral column points to a total body length just under 20 meters, with a mass approaching 60 tons. But every step in this process is transparent, and every conclusion is provisional. Researchers publish their equations, their error margins, and the assumptions that underpin each model. The size of Megalodon is not a settled fact, but a range, visible, measurable, and always subject to revision. The animal that once haunted ancient seas was immense, but its true dimensions remain bracketed by uncertainty, shaped as much by the limits of the fossil record as by the scale of its surviving teeth. In science, the shadows are as important as the outlines. A single coprolite, fossilized over millions of years, sits under the lens of a microscope. Within its hardened spiral, paleontologists have discovered fragments of bone, splinters from marine mammals, the remains of seals, and small whales. These microscopic clues tell a story of appetite on a colossal scale. Megalodon was not a scavenger picking at scraps. It was a hunter that fed at the very top of the food chain, targeting animals that themselves weighed several tons. The evidence is embedded in more than just bite marks. In teeth unearthed from ancient seabeds, researchers have measured chemical signatures, the ratios of rare isotopes locked in the enamel. Using a technique called clumped isotope thermometry, they have reconstructed the body temperature of this vanished predator. The results are startling. Megalodon's core temperature ran several degrees above the surrounding seawater, warmer even than the great white shark. This elevated heat is not a trivial detail. It signals a metabolism closer to that of a warm-blooded animal than a cold-blooded one. Warmth brings power. It allows for faster swimming, longer migrations, and the muscle strength needed to pursue swift, agile prey. But warmth is also a burden. Every extra degree of body heat demands more fuel. For a shark that could reach 60 feet in length and weigh over 60 tons, the energetic cost was immense. Each day required the equivalent of hundreds of pounds of meat, far more than a cold-blooded predator of similar size would need. The fossilized remains of prey, whale bones with deep ragged gouges, pinned skeletons with shattered flippers, speak to a diet shaped by necessity as much as opportunity. The scale of consumption is difficult to grasp. A single adult megalodon may have needed to eat the caloric equivalent of a modern orca every few days just to survive. Its jaws, lined with serrated teeth, were built for tearing through thick blubber and bone. But the ocean is not an endless buffet. The abundance of prey, the size of whales, the productivity of ancient seas, all set limits on how many giants the waters could support. In the chemistry of its teeth and the contents of its fossilized waste, the energetic gamble of gigantism is written. Evolution granted Megalodon the advantages of speed and strength, but chained those gifts to an unrelenting need for food. As long as the seas teemed with whales and seals, the balance held. But any disruption, cooling waters, shifting currents, a decline in prey, threatened to tip the scales. The very trait that allowed Megalodon to rule the oceans became, in time, its greatest vulnerability. Ocean temperatures began to fall during the late Miocene, cooling the surface waters that once stretched warm and shallow across the continents. Paleoclimate curves, traced from ancient sediments, show a slow but relentless decline. As the seas cooled, the structure of marine life shifted. Large baleen whales diversified, splitting into new forms that traveled farther and dove deeper, their migrations shaped by changing currents and food supplies. The giants that once gathered in coastal nurseries became less predictable, spreading out across vast distances. At the same time, new predators appeared. The great white shark, Carcharodon carcharias, emerged around 4 million years ago, its serrated teeth echoing those of Megalodon, but scaled for agility and speed. Fossil layers from the Pacific and Atlantic reveal a growing overlap, great whites expanding into waters where Megalodon teeth once dominated. Smaller, faster, and less dependent on massive prey, these sharks thrived in the restructured food web. Competition was not limited to sharks. Orcas and other marine mammals began to hunt in coordinated groups, targeting the same prey that sustained the largest sharks. The balance of power in the oceans was changing. With each cooling pulse, the boundaries of suitable habitat shrank. Coastal shelves narrowed. Productive upwelling zones shifted or vanished. The abundance of large, slow-moving whales, the backbone of Megalodon's diet, dwindled. These environmental and ecological strains did not act alone, but together they reshaped the world beneath the waves. The ocean's giants faced pressures from every side: colder water, scattered prey, and rivals adapting to the new order. The stage was set for consequences that would ripple through every level of the marine ecosystem. Along the world's ancient coasts, Megalodon nurseries once sheltered newborns and juveniles in shallow, protected bays. Fossil deposits in Panama, Florida, Maryland, and Spain reveal concentrations of small teeth, evidence that these sites served as vital breeding grounds for generations. Juvenile megalodons, measuring just a fraction of adult size, depended on these calm waters for survival before venturing into deeper seas. But as sea levels fell and coastlines shifted during the late Miocene and the Pliocene, the number of suitable nurseries dwindled. The loss of these habitats left the youngest sharks exposed, threatening the species' ability to replace itself. Last occurrence statistics from well-sampled sites in California, Japan, and the Mediterranean cluster around 3.6 million years ago. Yet the window is blurred by uneven sampling and possible reworking of older teeth into younger sediments. Some regions hint at later survival, but no reliable evidence extends beyond the early Pliocene. Scientists track the final appearances, but the true extinction remains uncertain, lost in the gaps between fossils. Speculation about Megalodon's survival in the modern deep sea persists in popular culture. The numbers do not support it. A shark of such size would need vast quantities of food every day, far more than the deep ocean can provide. No modern whale or seal skeleton bears the unmistakable scars of Megalodon's bite. No recent teeth have surfaced from the depths. The silence is telling. The story ends not with a single moment, but with a fading presence, recorded in scattered fossils and empty nurseries. The mystery endures, but the evidence draws the line between memory and myth. Today, over 80% of our oceans remain uncharted, far more than the land where Megalodon once thrived. As new species surface from the depths each year, the limits of our knowledge press closer. Some answers are lost to time, but the unknown endures just beyond the reach of sonar. In the deep, mystery is not the exception, it is the rule. What do you think still waits below?